All right, so sorry for the delay here. I want to thank Brian and everybody else for inviting me. I'm Brian Van Essen. I'm from Lawrence Livermore National Lab. We are a FFRDC in the United States. And I'm going to talk to you about some work we're doing on foundation learning for AI for synthesis knowledge, a project called Flask. The idea is that we're going to develop a foundation model to help us do molecular discovery. I want to thank the fantastic team we have here, and I actually want to note that we have a number of ETH alumni, Nikolai Dryden and Talbin Nunn. We've also had a student last year from ETH, as well as 3 students coming up this year. So again, while we are a national laboratory, we do have a lot of foreign nationals who work with us and collaborate with us, and we'd love to extend that going forward. So if you have questions, please contact me. So these are sort of what we do as a mission-driven laboratory. We have a lot of work in core competency, everything from inertial confinement fusion. You may have heard a couple years ago we created the first laboratory-controlled fusion environment with the National Ignition Facility, all the way to HPC, where we have the largest acknowledged HPC system in the planet right now, El Capitan. And so that really allows us to drive our mission science. And we have several core missions down there that really are why we exist and why we continue to get funded in these crazy days. So some of the key things we do is a lot about material discovery and design, and this goes everything from plastic scintillators that you use and optical crystals that you use in the National Ignition Facility, all the way to energetic materials that, again, we use in a variety of different ways. And so I'm going to talk to you about how do we think about bringing AI into the fold on developing new molecules and subsequently new materials. So you might say, well, what's the state of the practice right now? Well, there's a lot of work on using sort of standard forward propagating models where you can say, here's some constraints, let's project that in design space, and that's very interesting. And there's a lot of work right now on reverse design or inverse design where you say, let's optimize it for a property or two and then project out what kind of molecule you want. And we face a unique challenge in the space because most of the world is focusing on the red and the blue bubbles. They're pharmaceuticals and organic semiconductors. That's great, but as a mission-driven laboratory, we're really interested in this yellow bubble of energetics, which is critical for our mission needs, but not highly represented for in the community. And so we're going to be talking about data that is basically out of distribution from the majority of what the community is looking at. And so why aren't we seeing more success from some of these models here? And part of it is that we have multi-property optimization is pretty challenging for a lot of these generative models. How do we actually get feedback from the user, from a synthetic chemist into there? And how do we actually have models that develop things that are synthesizable? And so this is a project. It's a large strategic initiative that we have at the laboratory. It's about 18 months into a 3-year project. And as you saw, we have a number of performers. But the idea of this project was, can we use a data-hungry method such as foundation or deep learning AI in a data-starved regime where you don't actually have that many examples of the molecules and the synthesis routes that you care about. And so we're really trying to tackle this whole idea of developing a foundation model where it is good at general synthetic chemistry and then is specialized for our key mission need. And so if we think about the use cases we have, this kind of a quick flip chart through them, where there's a lot of things you might want to do. You might want to be able to just say, I have some properties, give me a molecule that adheres to those and has the properties close to what you asked for. You might want to do some lead compounds. We're here in Zurich, or in Lugano, sorry. I didn't sleep well last night because I'm time shifted, so we might need something better than caffeine. What can we synthesize that's better than that to keep us awake during the talks? But of course, if you ask any of your synthetic chemist friends, that's fantastic. You have a new molecule. Who cares? I can't make it. So they want to know, what is the synthesis route? How do they take it from design actually into production? And then finally, in the world of synthetic chemistry, there's a huge challenge in the space with PFAS chemicals, things that are incredibly toxic in our environment. So we might say we want to avoid a known route and produce a new one to make something easier to synthesize, safer, something like that. So how can we predict alternate synthesis routes? And with this project, as I said, we're looking at energetics. So really the question is, there are 2 key properties I'm going to talk about here. Our density of the molecule and the heat of formation, which is how much energy it contains in its bonds. And of course, like all good charts, we want to be up and to the right, where we have higher density and higher heat of formation. And that's really what we want the project to be able to do. So to get there, we can think about how do we represent molecules to these kinds of machine learning models. And you can go from ease of use on the left-hand side where you sort of have these 2D textual things. If you look at your 17-year-old daughter's chemistry textbook, you might start at the very top where you have a molecular formula. It tells you who's in the molecule. Or you might actually go to something like the SMILE string, which is a 2D arrangement of atoms that has a representation that can project to the graphical form you see in the 2D structure, but it's actually imprecise. And that imprecision is, in fact, quite a pain in the butt. You can go all the way to 3D representation of these models, but then, of course, if you're putting it into a machine learning model, you have to figure out how to represent that in a canonical form that is easy for the model to interpret. So there's a lot of challenge with that. As I said, in this part of the talk, we're going to focus on two properties, density heat formation, which are absolutely critical, and we have a 10,000 sample data set that we've been developing in part through experimental results, but also through a DFT-based pipeline where we're able to actually, use some traditional modeling and simulation to create a bunch of key properties, but DFT, of course, is very, very expensive. And so, as I said, so this talk is just a vignette of one aspect of the Flask project. I just want to focus on something cool that we're trying to get out of the door right now here. And the idea is that it's very hard to get models that behave well on out-of-distribution data. Another way to think about that is most AI models work really well on interpolation if they are trying to fill in spots within sort of the data set that they were trained on. But if you do extrapolation, most of them go off the rails pretty quickly. And we see that for these chemistry-based models as well. And so, but like you heard from the keynote yesterday, if you have physics-informed machine learning, you can add PDEs and other kinds of constraints to your model. We don't really use PDEs at this top level here for chemistry, but the question is, can we have chemically informed neural networks or AI models where you bake in some invariants that we know from, again, from our synthetic chemist friends that help us develop more robust models. And so that can be anything from invariant properties like bonds and what kind of atom types to equivariant properties like what the position and are they translational or rotationally invariant. So those are some of the things we're looking at. And we're going to show you a benchmark that we developed here that we call the benchmark for out-of-distribution molecular property prediction of machine learning models, BOOM. And the idea is that we wanted to actually know whether the model we were developing was going to be effective for the task at hand. And as part of doing that, we actually did this fairly comprehensive survey that we think is the first of its kind to actually see how well a wide range of models from everything from bespoke sort of GNNs or simple things like regression trees all the way up to transformer or hybrid models do at this kind of task. And we started with the two on the bottom right there, density heat formation, but then we extended this to the QM9, which is a quantum mechanics data set where there's a bunch of high quality DFT properties for a couple 100,000 molecules. And we want to see how well these models perform on this task as a baseline for what we were trying to do. And that's what we're going to talk about for the rest of the time today. So we found that it was critical because we really want to be able to have reliable understanding of like what are the models doing and how are they succeeding or failing, because again, energetics are out of distribution with respect to the main body of synthetic molecules, and so this is a fundamental challenge for us. These are the models that we evaluated here. They're basic architecture, so everything from random forest all the way to hybrid equivariant transformers. What do they capture in their representation? So things like RDKit is a popular toolkit for representing these things. SMILES, you'll see a lot of those, and those are very natural for large language models to work with, all the way to ones that have very rich atom, bond, and pairwise distance interactions, and what their symmetry properties are in the number of parameters. And so what you're going to see is that they vary in quite interesting and different ways. When we talk about out of distribution, what we've done is we've taken both our 10K data set and this QM9 data set, and we have partitioned them so that for each property, we have an in distribution and out of distribution set, and as well as a training set that captures the in distribution part. So shown here in orange is what our train set is, and then our held out evaluation set. Again, we have hard partitions, and it's done by property value. So it's not necessarily the same molecule is out of distribution for everything. It's out of distribution for that particular property, say HOMO-LUMO gap. So just a sort of top level summary here. If you look at a few of these models here, what you can see is that they don't, well, how well they do based on RMSE varies quite a bit, where you go all the way from 34 on out of distribution to 9,000, which is really not doing well for that particular thing. And then there's the R-squared coefficient as well. If you look at a parity plot on the right-hand side, we're showing the true density on the x-axis, the predicted density on the y-axis, with the in distribution shown in orange, which is always going to be the middle of the plot, and the blue distribution tails on the upper and lower bounds. And what you really want to do is, this is actually a Kim-Prop model that's doing reasonably well on density, where they're reasonably aligned on that that parity line. So that's pretty good. What happens when you start, this is just if you look at the density for a wide range of them, so I'm not going to go through each one of these, but you can see when they start looking flat on the ends, that's bad. So here we have the random forest, which is not terribly chemistry informed. Kim-Butter and Kim-Prop don't do well at all. And then if you go to ones that have either more structural information, like a graph representation in their 2D representation, or all the way going to 3D, where they have like DFT-based coordinates provided for them, or the equivariant transformer, they do much, much better on density. So that's great. Okay, let's do this for heat of formation now. One of the things we care about, again, the more basic sort of smile-based ones do not do well. They don't generalize outside. And then the structural ones and the 3Ds do a lot better. Okay, so are we done? Well, okay, let's look at the whole set of data, and the answer is no, which is why we're here today. So we have density heat of formation, which we do care about, and what we're showing here is for all of the properties that we care about, as well as the QM9, we have rescaled their RMSE so we can plot it on the same thing. I think we've actually dropped off the regression transformer, which is a model we were looking at, because it sort of blew things out of the water. And orange is good. That's a low RMSE, so that's the in distribution. And when the blue is close to that, that means the model's predicting close to its in distribution error. And so you can see, again, for heat of formation and density, it does pretty well. But for all of those other properties shown with the blue really up at that sort of midpoint line, particularly like HOMO, LUMO, and GAP, as well as mu, they really aren't doing well. And so we're not able to actually have a model that is predictive for these kinds of properties. And when you think about synthesizability as well as general performance, this really limits our ability to extrapolate. So let's go a little bit deeper and see what's happening. If we think about what we see with representations here, there are sort of three main classes at this point. There's the smile strings, which is sort of the most easy to represent. That's this sequence of characters that you put down that roughly capture the structure. Okay, great. You can see in red that it's pretty much doing the worst on every single property that we care about. So that's not terribly good. Again, 3D coordinates are actually pretty good for in distribution and out of distribution. You can see they're mostly all black, so they're pretty decent. But again, they can be pretty challenging to find good canonical representations, and actually getting good high-quality 3D coordinates is challenging. And then explicit bonds is sort of like having a graph representation is a pretty good middle ground, and we're going to come back to that at the very end of the talk here. So having that structure and geometry really does help. And this is sort of, again, when we think about the physics-informed neural networks, in some ways this is a chemistry-informed representation where you're baking in some of that implicit knowledge that you have as an inductive bias into the model itself. We also want to explore what happens if you deal with pre-trained models. So this is a mole former here, which was trained on 1.1 billion labels, unlabeled smile strings, and then we elevated it. So the solid lines, either blue or orange, are if we pre-trained the model from scratch, just on the test or on the train set. And then the hashed line variants of those are if we took the pre-trained, The solid colors are from scratch models. The hashed lines are pre-trained on 1.1 billion unlabeled smiles and then elevated and fine-tuned with our training set. And what you see is it doesn't buy you a whole lot. There's a couple places where it gets a little bit better, but this sort of standard pre-training method is not improving. And we saw this for mole former, Kim-Butter, and regression transformer. We did see that doing some data augmentation really does help. So adding a couple of out-of-distribution samples, anywhere from 0 to a couple thousand, on the x-axis shown here, can dramatically bring down the RMSE of the out-of-distribution samples on the y-axis, or not dramatically, by some amount. So that's pretty good. And it varies based on some of these properties. So like mu is actually pretty obnoxious there. But this does give you hope that you can actually compute your way out of this sum by doing some DFT pipelines or experimental pipelines to get through part of this. So that's exciting. But we do see that while 3D is an improvement, it helps in some situations. And it turns out that you can sort of think about this in terms of extensive versus intensive properties. And so the intensive ones that are typically more challenging are the ones that are sort of not based on the shape and volume of the molecule that's being taken up. So that's why the 3D doesn't help as much. And those are shown there on the right-hand side. We also did look at a more modern model called Modern BERT, which came out during the course of this project, and it has some key innovations. In particular, they have a new type of pooling bias, which really actually helped. And what you see is if you compare Modern BERT versus other two transformer style, Kimberta and Molformer, which were developed specifically for chemistry, you can see that in green, Modern BERT is doing way better on many of these properties that we care about. But again, it's not all good. These sort of intensive properties like HOMO, LUMO, and GAP and mu are still quite challenging. So we don't really have a solution for that. So what have we learned from this? Well, okay, one is that getting 3D information is really a key part that's very useful in doing strong molecular representation. Pre-training helps some, not a whole lot. Using DFT to actually compute some samples in your outer distribution set can really help. And having that, I mean, the bottom line here is having that inductive bias so that chemistry-informed representation and thus model can really help with learning some of these latent features. This is going to take a step back, so we did that on sort of the standard set of existing work there, but we always get asked, why not just use a standard LLM? These things are taking over the world. They are great at everything. Well, they think they are, and if you ask them, they will tell you they're great at everything. So we've tried this particular task with basically all of the modern reasoning models out there, and they will give you incredibly confident answers that are absolutely wrong. So there's some room to grow there. So for example, if we take Meta's Llama 3.3, and we sort of do this heat of formation task right out of the box, you can see the parity plot up there on the right-hand side, where it's just a flat line. Maybe it's hard to beat. I don't quite know. Not good, but there is hope, of course. And you know, the great thing about these new models, especially the large language ones, now is you can do things like chain of thought reasoning. You can also do reinforcement fine-tuning. So there's a lot of techniques to add in data to make it better. And so we just have a new version of this of our Flask baseline model. We were a pre-trained model. Now we're going to use an open weights model where we're fine-tuning it. And one of the things we like about this is that actually with a moderate amount of data on heat of formation, we're able to get that parity plot on the bottom right here. So that's a meta plus fine-tuned model. So that's pretty exciting, and that's getting very competitive results on that one property. I will tell you, this is work in progress. As I said, we're 18 months in, so we're still working on all the other properties and getting to train and learn in a similar fashion, but that is exciting. One of the things that we are intending to explore is the fact that, again, as I said, better representations matter. We know with these kinds of large models that you can actually teach them a handful of languages and you extend them to new languages. So, you know, you can take things like, you know, your English to French and whatnot, and you can actually add it, give it some examples, and you can probably make it learn Klingon or Old Elvish. And it can do that with a handful of samples really quite effectively. So one thing we're exploring is, can we give it a new representation? Because when we look at what it's doing, when you give it these smile strings, it is trying to reconstruct the connectivity graph of the atoms within the molecule, which, by the way, we already know, so we should tell it that. So there is a promising representation that was published about 18 months ago. It was not ours. It's called Atom and Smiles, but it is a very nice representation that tries to combat the two key challenges that we have with smile strings. One of which is, if you look on the right-hand side, is it turns out that while smiles are supposed to be canonicalized, they are not unique. And so that is a smile string that has two different molecular representations, which I'm told matters. So that's important. But the second thing is this is baking in the neighborhood information for each atom in the SMILE string, where you basically break it down. So you take your original one, you take each molecule shown up in the canonical SMILES representation, and you add basically this neighborhood information. Everything after the first semicolon is sort of like who your neighbors are, and that gives you a unique encoding that has captured some of that key information. So that's great. You can now differentiate like which carbons they are and which oxygens. So this is really cool. It turns out that this has its own challenge. We encountered this first when we tried to actually do a pre-trained or a trained from scratch model using this representation, which is the vocabulary explodes. And if you look at any single data set, you actually probably have very little overlap with subsequent data sets, because your token is now, for every atom, the entire neighborhood with it. And so you lose some of the commonality that you really want. And so, we have this idea here where if you go to the far right-hand side, you're into SMILES. They're fairly small vocabularies, it's like 70 characters or something. But of course, they aren't always unique, and so that's a challenge. If you go to the far right, you include every molecule as a token. Well, that's bad. Atom and SMILES is just to the left, just to the right of that, where again has a very large vocabulary set. And so we created a new one called TALS, which is based on the Atom and SMILES representation, but has a more robust, extensible representation, where basically for the encoding, you basically have you break down the neighborhood information as a set of tokens rather than a unique one. So we're evaluating right now whether telling a large language model that knows SMILES to learn TALS or AIS and be able to say, this is how you should think about reasoning with these molecules, and see where that is going to go. Okay, so man, am I cooking through this? I'm going to be on time and with some time for questions here. So what have we learned? It turns out that good out-of-distribution performance is not impossible. There are models that do it well for many tasks, but not all. There's definitely open room for research here. Being able to have that inductive bias, give it what we know, right? Don't make it learn all of chemistry from scratch, is way better than just saying, like, here's a bunch of characters to figure out what we meant by that. We do see that normal pre-training is not as helpful as models with the high induction bias, the high representation. So again, 3D can help, but we're looking at some different representations. Modern BERT is a fresh shot in the arm there about something that's a transformer that actually really does quite well. And we're still investigating why it does so well, because the techniques are not necessarily intuitive about what makes that better. But there is definitely an opportunity to innovate in the molecular representation, especially when we're using these kinds of large language models. So we are publishing both the data set, the way we do the test chain split, so we actually have the repo. It's going to be published as well as an archive paper, and we're going to submit it to a journal so that we can actually share this. And part of this making a good benchmark is having a repeatable benchmark, and so we want the community to be able to adopt that, including the exact way in which we split the data sets so that the numbers are comparable. So just to wrap up here in record time for a 40-minute talk, which we're going to do in 22.23 minutes. Flask, the whole goal of this project is to create a molecular foundation model. Today I focused on how do we do the assessment and evaluation of these models for a particular challenging aspect, which is the fact that energetic molecules are out of distribution, and so we really wanted to focus on that and get some traction with how to understand that. The idea is that this foundation model is going to be usable across a wide range of our portfolio, but also the training techniques. How do you actually train these things at scale using things like leadership class computing? So we're doing a lot of this work on El Capitan, or the unclassified baby sister Tuolumne, which is number 10 on the top 500 list. And how do we optimize for AMD architectures and stuff like that? We can talk all day about that as well, but I didn't put it in here. And really, we're focused on molecular discovery and design, and that's a pathway to materials, which is, in fact, I think a much more challenging problem. But we also, in this project, I didn't get to talk about it, we do actually have, we're bringing on board robotic chemistry systems like ChemSpeeds or Unchained Labs, where you can have these robotic laboratories, and the idea is that you could actually drive them from this kind of foundation model, where not only will it tell you a multi-step synthesis route in the end, but it will tell you how to actually use your system to do that automatically. That's what we're driving for, and I guess I have time for questions. Thank you very much.
Okay, any questions for Brian? Okay. I know that's a general question, but can you talk a little bit about the computational complexity? How much of this work requires El Capitan? Just some general hints on there.
Yeah, so I mean, when we started the project, we thought we were going to be able to scale the whole thing all the way up because the design space could be so large. We got a huge amount of traction in our first generation model, which was based on regression transformers and then all the way up to sort of llama models. And we were training those up to 8 billion, no problem, but that didn't require that much. And it turns out that those models sort of petered out for a number of reasons we can talk about over a coffee. And so we're now pivoting to using these open weight models. And so part of this is can we work with 100 billion parameter or several hundred billion parameter models? Those are going to require a reasonable amount of compute capacity, a couple terabytes of GPU memory. It's not necessarily going to scale all the way up to LCAP unless you want to start doing ensembles where you can really sort of drive a complex workflow where you are doing DFT, elevating molecules in the loop, and then driving them back into the training as well in sort of a reinforcement fine-tuning loop, which is actually where we think we want to and need to go. So I don't think it's going to take all of LCAP, but it's going to take a reasonable chunk of a leadership class system. So, yeah.
Thank you for the super interesting talk, first of all. You mentioned a few interesting points in your presentation. The first was that you're working with a data set of about 10,000 molecules. You showed how some of these models struggled with sort of out of distribution samples, and you mentioned that it's the models that are struggling to sort of learn the distribution and extrapolate data. Now, when you go especially to the 3D representation of your molecules, especially if you think about the representations that are used for classical molecular dynamics, very, very high dimensional representation. So the first thing that sort of what you discussed brings to mind is how do you know that the issue is really that the models are struggling to learn and extrapolate data? That it's not simply an issue with the input dimensionality of your problem being too large, and so you're kind of suffering from a curse of dimensionality where you don't have enough samples to represent your whole phase space or configuration space sort of accurate enough way.
Right. So, good question. I think first off, we also have splits on not just our 10,000 data set. So the 10,000 data set is a set of molecules related to energetic molecules, right? So they're not all energetic, but fundamentally that is a part of the synthetic chemistry space where there are just not that many examples. So whether or not we don't have enough data is not really the question. It's like, what can we do with the data that we do have? And so we may be suffering from just the model hasn't seen enough to learn about that. When we look at things like QM9, that's a couple 100,000 molecules that have been simulated there. Some of the models that were trained that also didn't perform well were trained on several billion molecules. And so it may be that we just need more. But of course, if your answer is you need more and you get that from crystallography, light sources, and DFT, you're kind of screwed if you need billions of those. So we can't compute our way out of that using brute force techniques. We've also seen other models here. One I didn't show, there's an interesting model that came out during the course of the project that we've been evaluating called MACE, which is a graph neural network, sort of more traditional approach that's designed to be a fast surrogate for many DFT-related calculations. And so, you can think about these sort of techniques where can you get enough reasonable quality data from a tool like that on a large set of molecules to help inform the model generally how to interpret the DFT-related data, and is that surrogate of high enough fidelity to allow better extrapolation? I think it's going to help, but I think it's not going to be a replacement for better representations. I think it's going to be we have to do both.
Thank you very much.
Yeah.
Got time for one more, okay?
That mic I just shout. It's not that much of a help.
Like mixture of experts type models instead?
We have not had a chance to play with mixture of experts type models. That's a great question. And part of that is just, we didn't grow an MOE from scratch. And at the time, there was no available open weights model that we could use. Llama 4 dropped this weekend. So after we do a Gordon Bell submission on next Tuesday, we'll be looking at that open weights model and how MOEs can do better. And that provides a lot of opportunity to think about, can you differentiate parts of the model? Can you elevate them in an appropriate way? But it'll be an interesting challenge to think about how we fine-tune and train those.
Here, no? I don't think it works, right?
I'll repeat the question. So, yeah.
So, like, you might have one part of the model which is going to be sure that you have around maybe smiles that are more general. Have you looked?
Well,
How much
okay,
research on how to
so
combine
the
these
question,
things?
the question is, one, have we looked much at mixture of experts yet? Yes, that was the first question. The answer is no, not really. And as we start to look at mixture of experts, can we think about some where there is an expert for things like smiles, an expert for things like the literature that's supporting that? And I think that that will be, that is a great area of research that actually may require you to train a bespoke model from scratch to get that level of differentiation between the experts. The other question is, this is an open research question, is can you take an existing model with a mixture of experts and add in new experts and retrain the router as well without losing everything else that made that model good to begin with? So I think that's, again, an open question that we intend to be evaluating, but we have not yet had a chance.
All right, thank you, Brian Van Essen.
Thank you.
All right, so